Welcome to Adding Houdini to your arsenal part 5. This time I want to extend the working with clones setup. This is where we left off last time. If you remember, we used this spherical falloff node here to create a spherical falloff attribute, and later on we used this attribute inside of this effector VOP to do something to our template points and thus to our clones. That is nice, and it gives a nice effect here, but the falloff is created spherically, which is cool, but to really make use of this system we need different falloff shapes. So let's implement a linear falloff now. Because of the splitting of this setup in two parts, creating the falloff and then using the falloff, implementing another falloff is easy. We just have to put down another point VOP that we call linear falloff. Let's color it yellow, like the spherical counterpart, and connect the grid to the very first input. And now we need some defining geometry. We use the sphere for the spherical falloff, so for the linear falloff we want to use a line. So put down a line sub. This line sub just generates a line, one primitive with 2 points. If I turn on point display, you see point 0 and point 1. And you can rotate these points and transform them however you like. The line is defined by the origin. This is a point where the point 0 lives. Then we have the direction and the length. Let's keep this length to 1 for now. To be able to move this around, we can append a transform, like so. And now we are able to rotate and move this line however we like, as you can see. And this will be connected to the second point of the linear falloff. Make the linear falloff visible. Turn off point display and dive inside of the linear falloff. This time we have 2 points that we can work with, the first and the second point of the line. So let's import them using an import point attribute that we connect to port 2 here to read from the second geometry stream. And then we need a constant, like last time. The constant will be of type integer, because we want to set the point number with this, and this will import p, so the position of point 0 of the line. But this time we want to duplicate this by dragging with Alt. The op input 2 stays connected, and the constant will be switched to 1 here. Now this node imports the second point of the line. We have the first point and the second point of the line. That is great. But how do we map falloff values to our clones based on these 2 points? Let's quickly jump to Photoshop to think a little bit about the theory before going on to implement this node. So let's quickly think about what we have. We have a line somewhere in space, like so, that is composed of 2 points, the starting point 0 and the ending point 1. And if I subtract these 2 points, I get the vector here. Let's call it L. This is this vector pointing to 1 here, if I subtract 0 from 1. And I have a clone somewhere in space. Now, what I want to do is I want to map the position of this clone onto this line. And then I can establish a relationship between the length of this line and the length of the projection of this clone onto the line. So what if I calculate this vector here that goes from the first point to the clone? I could do this if I say this is clone, so the vector clone. I can do this by stating clone minus 0 or minus p0. Let's say this is p0, p1. So this gives this vector here. And now what I want to do is I want to project this vector onto the vector L. To understand projection, you can think of a light shining onto vector L, orthogonal to L. And then the shadow that this vector casts onto the vector L is a projection. So if you form a right angle here, then this vector here is a projection of this vector to L. Let's color this to make it visible. So this pink vector here is a projection of this vector to our vector L. And now I can see if my line encodes a fall-off between 0 and 1, that I just have to compare the length of this projected vector to the vector of my line to find the fall-off value. So if this happens to be exactly half of the vector, the fall-off will be 0.5. If this projection would be exactly the same length as vector L, the fall-off would be 1. And if this would be 0 or smaller, then the fall-off would be 0. That is a principle. What's left is to think about how we could mathematically project one vector onto another one. And the answer is using a construction called the dot product, or the inner product, or the scalar product of two vectors. So let me explain to you what the dot product is. The dot product is one of two ways of multiplying two vectors, the other way being the cross product, but this is for another video. The dot product can be calculated in two ways. The first way is to multiply the components of the vectors together and then add all this up. So if you have two vectors, A dot B, dot is a symbol for the dot product, then this means that you take the individual components of the vectors, so AX times bx, and then add this to ay times by plus az times bz. So that's an easy formula to calculate the dot product, but it does not give us any intuition what this means. The other way to calculate the dot product is that the dot product of a vector A dot vector B is the length of A times the length of B times the cosine of theta. And theta is the angle between the two vectors. Well, that is a little bit better regarding the intuition, because at least it is somehow related to the angle between the vectors. If you look at these formulas, the very first thing that you see is that the dot product turns two vectors into a scalar. So if you look at this definition here, you have the length of A and the length of B, which are scalar quantities, and the cosine of an angle is a scalar too. So the result of the dot product is a scalar. But what is the geometric interpretation of the dot product? The geometric interpretation normally is far more interesting than this mathematical definition. So if you have this vector here, called A, and a second vector, called B, then the dot product is the multiplication of the length of the two vectors, but only as far as they go in the same direction. So what happens is that you project A onto B, like so. Then you end up with this projection of A. Let's call it A with a little tick here. And then you multiply the length of this projection and the vector B. And that is what the dot product is. It's the multiplication of the lengths of the vectors in the same direction. So it takes only the same direction into account. The funny thing is that it works the other way around too. So if you have vector A here and vector B here, you can, if I extend this vector here, you can project vector B onto vector A and then multiply these two, and you end up with the exactly same thing. So this gives us a little bit of intuition of the dot product. But why does this work? To understand what's happening, we need some trigonometry. Remember that trigonometry is dealing with the relationships inside of the circle. So let's draw a circle, and here is a center point, and here is a radius. And there is this nice mnemonic called SO, CA, TOA. And that defines the three trigonometric functions sine, cosine, and tangent. If you draw a triangle here inside of this circle, then you have here the angle theta. And you have these sides, and all of these sides have names. This one here is called the hypotenuse, this one is adjacent, and this one is the opposite side. And if we know that, we can use this mnemonic to say that sine of theta is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse, and the tangent of theta is the opposite over the adjacent. And now remember our formula for the dot product. So vector A dot vector B is the length of A times the length of B times cosine of theta. So if you take the hypotenuse here and say this is the length of A, for example, then the cosine will give us this length here, because the cosine is defined as adjacent over hypotenuse. And if we want to know the length of the adjacent is cosine of theta times hypotenuse. And hypotenuse in our case is the length of A. So that means if I take the hypotenuse times cosine of theta, I end up with this adjacent. And that is really a projection, because it projects this line here down to this line. And that is why the dot product is doing a projection. So what happens is, if you have two vectors here, A and B, think of it that way. If you rotate the entire picture such that B is horizontal, and you have A here, like so, then you can do exactly this. You can just calculate the cosine of the length of A, and you will end up with this portion here, which is the projection. So this is the reason why it's projecting. So hopefully this helps us better understand what we can do with the dot product. So if you have A dot B, which is A, B, cosine of theta. If you want to have a projection of one vector to the other vector, you can do the following. So let me redraw our picture, A and B. If I just use this, I get the projection and then the length of the projection multiplied by the length of B. But what if I normalize B, such that B has the length of 1, so unit length? Then this term here is just 1. So say this length here is 1. Then this formula is the length of A times cosine theta. And that means that this really just gives me the length of the projection of A, because the length of B does not play any role anymore in this equation. And if I now use this vector B here, let's call it B hat, like so. That indicates that B is of unit length, so it's normalized. It's normalized B. If I now take this vector, which is just the direction with length 1, and multiply this quantity times B hat, and then I get a vector that is exactly this length here of the projection, but in this direction. So this gives me, let me color this. This is vector, let's call it C, and C will be this vector here. So while the dot product is dealing with scalars only, so only gives us length, multiplying with a normalized version of the second vector gives us a vector in this direction. And now I have really a projection of this vector onto this vector, not only a projection of the length. That's a very important and useful concept. The second thing is that I can use the dot product to calculate the angle between two vectors. So if I have a vector A and a vector B, and here I have the angle theta. So let's rewrite this formula. A dot B is the length of A times the length of B times cosine of theta. So if I'm interested in cosine of theta, what I can say is cosine of theta is A dot B divided by the length of A times the length of B. And if I now want to know theta, I can use the inverse function of cosine, which is arc cosine. So arc cosine of A dot B divided by the length of A times the length of B is theta. And using this formula, I can find the angle between two vectors. And now have a look what happens if I normalize both vectors. Then the length of both vectors will be 1. So this term here will be 1. And then this just goes away, because dividing by 1 is not doing anything to the term. So that means if I normalize the stuff, I end up with a simple formula. Arc cosinus of the dot product between the vectors is the angle between the vectors. Very useful in many cases. And now that we know that, you can easily see that the dot product has a very interesting property. If you don't want to know the angle exactly, but just want to know if the two vectors are pointing roughly in the same direction or not, you can just look at the sign of the dot product. Because if two vectors A and B are roughly pointing in the same direction, the dot product will be positive. If the vectors are orthogonal, so you have a right angle here of 90 degrees, then the cosine of theta will be 0, so the dot product will be 0. And if the vectors are pointing in different directions, like so, say this is A and this is B, then the dot product will be negative. So by just looking at the sign of the dot product, you can find out a lot of information about your vectors. If they are pointing in the same direction, if they are orthogonal, if the dot product is 0, or if they are pointing away. So you see these three uses, being able to project one vector onto another vector, or calculating the angle between two vectors, or just stating if the vectors are pointing into the same direction, are all very useful concepts of the dot product. So now let's implement this linear falloff. First we want to create the vector by using a subtract. So if I subtract 0.1 and 0.0 of my line, I get the vector between the 2 points. That is the vector between the 2 points. And then I want to duplicate this subtract node with Y and drag. You can delete all the connections. And now I want to subtract the position of all the points of my grid here from the very first point of my line. So now I have two vectors here. First, the vector of the line itself, and then the vectors from the point 0 of my line to the position of the points. And now I can compare these two vectors using the dot product. So lay down a dot node, dot product, and do a dot product between these two quantities. Now this gives me the projection of the vector of the point to the point 0 onto the line itself, but then multiplied with the length of this line, of this second vector here. And to transform this result into a range between 0 and 1, I want to do a trick and use a dot product again, but this time dot the line with itself. Because what this gives me is the maximum length. If the projection has exactly the same length as the line, the result should be 1. So if I do a dot product between the line and itself, it gives me the maximum length that this projection can ever be. So that is my maximum length. And to now transform the result of this dot product into a range between 0 and 1, I just use a divide. And I divide the result of this dot product by the maximum length that can appear. And now I have everything in a range between 0 and 1. And the last thing I want to do is to clamp this, because as I told you, the dot product can get negative, and I don't want that. Whenever the projection is smaller than the second vector, I want the falloff to be 0. And whenever it is longer, I want the falloff to be 1. So I clamp this result to 0 and 1. And that can be used as our falloff. So create a bind export and call it falloff, like so. So, and now let's make this color visible and connect this here. And let's see what happens if we now move our line around. You see, it's working. I have a linear falloff. All the values that are less than the first point are 0, and all the values that are higher than the last point are 1 due to the clamp node, and in between I have a gradient. And I can rotate this, and the falloff gradient happily rotates with the line. And if I go to the line sub and make the length smaller, you see that the gradient gets smaller too, because it always maps between the 2 points. So now I have a very nice linear falloff that can define a global gradient in 3D for my points. And if I now make the copy to point visible, you'll see that I have this effect that I had before, but this time with a linear falloff. So before we stop, go to the spherical falloff and copy these 2 nodes that are dealing with the noise, because this noise is something that might be beneficial for our linear falloff too, and if I paste them here, they get immediately connected because Houdini understands that they used to be connected to P. And if I now use these warped points instead of the original points, I get the same noise effect on my linear falloff. And this looks quite nice because now I have a noisy linear falloff. Let's make it a little bit longer again, say 1. And you see that I now have a very nice noised linear falloff. So now we have 2 falloff types, a spherical falloff and a linear falloff, which are the basic falloff types. To easily be able to switch between them, let's introduce a switch node. And move this stuff a little bit down such that we have a little space here, and then connect both falloffs to the switch node. And now we can control which falloff is used by just moving this slider here. So now we can switch between the spherical and the linear falloff. Although coming up with analytic falloffs like these 2 is a lot of fun, it's sometimes a little bit tedious to implement every single falloff by hand. So there is a way in Houdini to use whatever you want as a falloff. You can use objects. So create a box that we want to use as a falloff. And to be able to use this as a falloff, we want to turn it into a volume, into a special kind of volume called a signed distance field. You can do this by a node called ISO offset. The ISO offset node converts its inputs to a volume, and as soon as I make this visible, you get a fog volume. So this is just a 3-dimensional pixel image. It's a box filled with little boxes, and these boxes get a float value. And the fog volume is just saying, make the voxels, the little boxes, 1 wherever the object is present, and make them 0 where the object is not present. You can middle-click on this node and get this information panel, and this tells you the resolution of this 3-dimensional volume, and it is currently 10 by 10 by 10. We can increase this resolution if we up the uniform sampling divisions to say 50, and you see that it's now a lot more defined. But we don't want to go with the fog volume. What we need is a signed distance field. So go here to output type and switch to SDF volume. SDF stands for signed distance field. And then you get this shaded preview of the volume. And what you see here is just the ISO surface. A signed distance field does not store 0 and 1 values inside of the volume, but it stores in every voxel the distance to the nearest surface. That means where the surface exists, the values in the voxels are 0. And if I only draw these voxels, then I get the ISO surface, so the surface where all the values are 0. But to the outside and to the inside, I get gradients of values, because, of course, the distance to the surface increases or decreases into the two directions. And I can make use of this information to generate a fall-off. To do this, I need a node to transform these volume values into an attribute on geometry. And there is such a node called attribute from volume. Attribute from volume. This node expects two inputs. First, the geometry to which the attribute has to be applied, and then as second input, the signed distance field. So connect our grid to the first input, and then our signed distance field to the second input, and make this attribute from volume visible. And at the moment, it is transferring the values from the volume to the attribute CD, so to color. Don't see anything, because this grid happens to live completely inside of my box. But we don't want to do that. We want to map the values from the volume to fall off. So let's do this. Of course, the color vanishes immediately. And now let's connect this to the switch and go to the switch and move this to 2 and make the color node visible. At the moment, everything seems to be 1. And that is due to the mapping here. Let's use this mapping tab of the attribute from volume to define the mapping of the values. Let's tick this map volume to value on, such that we get this ramp here. And then let's decrease the range 0.2 to 0, because the inside, by convention, has negative values. So if we are using a Houdini volume, and the ISO offset is generating a Houdini volume, all the values inside of the volume get a negative sign. And if I want to use the inside of this volume as a fall-off, I have to remap my range from the negative domain to 0. And I do this at the moment. And here I have values of 1 inside of the volume, and then values of 0 outside of the volume. And I want it the other way around. So just reverse these knots on our curve, and we have it the other way around. And if you now want to transform this, you can lay down a transform. But be careful. Don't put the transform here after the box. Because if you transform the box, the ISO offset will have to generate the volume for every varying transformation. So whenever you transform the box, this node has to cook. If you put the transform after the ISO offset, you just generate the volume from the box and then you transform the volume. And as volumes are just standard objects in Houdini, that's not a problem whatsoever. So if I do that, I can just move my fall-off around as with my other fall-off types. And with this attribute from volume, you can decrease this input range value here to make the fall-off smoother, so to take more values into account. And you can alter this curve here to your liking. So let's color this attribute from volume yellow too, because it is a fall-off type, sort of. And if you now, for example, create a torus and put it here into the ISO offset, you see that you are generating a torus fall-off. So by using this technique, you really can use whatever geometry you like to generate a fall-off inside of Houdini, which is very versatile and comes in very handy.